Hi all, welcome to the session of Power Electronics and Instrumentation. So in today's session we will be going to the next module, that is the phase control converters. Along with this we have the DC choppers also. So the two different converters that we have studied in the converter classification, we are going to study here in this module 2. Okay. For now we will start with the phase control converters. So phase control converters are also known as the rectifier circuits. Rectifiers, why do we call it a phase control? Because we are going to, phase is nothing but an angle. So we are going to control the angle of the device. Okay. So by controlling the angle we are going to achieve a controlled output. So we call it as a phase controlled converter. So here the rectifier is the device that we are using. Rectifiers means what does it perform? What is the conversion that is of power that is taking place? A rectifier converts an AC input AC signal to an output DC signal. So AC to DC converters are known as rectifiers. In specific, since we are controlling its angle, it is known as the phase controlled converters. Okay. So rectifiers, as we have already discussed in the module 1, that is, these rectifiers are almost used in most of the battery chargers, lighters, heaters, small motor drives. So wherever we are going to use the DC as the input, DC input suppliers, in all these cases or applications we make use of a rectifier. Okay. Usually this rectifier is a very simple circuit. Why? Because here in case of rectifiers, the process of turning off, that is, we have already discussed about the commutation process. In case of rectifiers, what will happen to the commutation? What type of commutation is it? Since the input is an AC, so always the rectifiers follow a natural commutation process. Since we are using this natural commutation means what? Whenever there is an AC signal, alternating signal, then depending on the position of the device, whether we have placed anode to cathode or cathode to anode, let us take an example of a thyristor. So depending on the position of the device, for one half the device will be in its on state and automatically the other half cycle, then what happens? The other half cycle of the input, automatically the device goes off. So no need of using an extra circuitry in such a case, in the case of a rectifiers. So this rectifiers is usually a very simple circuit. Why? Because mainly it follows the natural commutation process. No need of having an extra circuitry and force it to go to the off state. So commutation circuit is not required. Hence this circuit, rectifiers, is a very simple and easy to design circuitry. Okay. Now we have understood it is converting a input AC signal into an output DC signal. Okay. How are we classifying these rectifiers? So depending on the different type of devices we are using, rectifiers can be classified as uncontrolled rectifiers. Uncontrolled means which is the device we know which is an uncontrolled device, uncontrolled both in on state as well as in off state. Which is a device? That is nothing but a diode. So in the circuit, if you are going to use only the diodes, we have already seen in the explanation in the previous module, if you are using only diodes, you are not going to achieve the controlling action. Just positive cycle, it goes on, negative cycle, it goes off, but controlling is not done. So the power will flow from 0 to 180 degree. There will be the loss of power if you do not want the complete power from 0 to 180 degree. Okay. So if you are going to use only diodes in your rectifier circuit, then such type of classification is known as uncontrolled rectifiers. Is it clear? Next, fully controlled rectifiers. So in case of fully controlled rectifiers, either we will be using the family of thyristors. Usually we prefer the thyristors. Okay, we can use the power transistors also, like the power BJTs, power MOSFETs. We can also use that is also fully controlled. You can control both on and off, but since it is an AC signal and we have a thyristor which is most suitable for the rectification process, we prefer the thyristors. And in the rectifier circuit, if you are going to make use of the thyristors, which is going to be controlled during its on state with the help of a gate signal, then such circuits are known as the fully controlled rectifier circuit. Okay. Now, if you are going to use a combination of a diode as well as a thyristor, then such type of circuits are known as half controlled. Half controlled rectifier circuit, which will consist of a combination mixture of diodes plus thyristors. If in the circuit we have a combination of diodes and thyristors, then it is known as half controlled rectifier circuit. So this is a general classification of the rectifier circuits. If you are using an uncontrolled device such as a diode, it is known as uncontrolled rectifier. If you are using a fully controlled means the on time you are going to control. Then if you are using a thyristor in the circuit, it is called as fully controlled. If you are going to use diodes and thyristors, then it is known as a half controlled rectifier. Okay. So this is the main classification. Now let us take an example of an uncontrolled circuit, rectifier circuit. So in this case, if you are going to use in the circuitry here, if you are going to place the diodes, what is going to happen? The power flow is only from AC to DC. Okay. In the previous sessions we have studied about how we are going to get the output voltage. So if we are going to use only diodes here in this case, okay, the power is going to flow from AC. Power flow is from input AC to out. This is the input and this is the output, AC to DC. AC input to the DC rectified output. If the power flow is only from input to output, such type of rectifier circuits are called as unidirectional. Means the power flow is only in one direction. So under unidirectional rectifiers, we can have uncontrolled as well as half controlled rectifiers. So this uncontrolled and half controlled rectifier circuits, what we have, allows the power to flow from the input to the output only one direction. Hence it is called as unidirection. So unidirectional rectifiers are uncontrolled and half controlled, whereas fully controlled rectifiers, we will be using two thyristors in such a case that at one switching point we are going to allow the DC to flow back to AC. Okay. So when we are using the fully controlled rectifiers, okay, only for such a case it is known as bidirectional controllers. At some switching points, generally we have the power flowing from input AC to output DC. At some switching point, the DC is flowing back to the supply, input supply. So in such a case, that case is possible only when we are making use of a fully controlled device, and hence fully controlled devices are also known as bidirectional rectifiers. So this is another type of classification based on the flow of power from input to output and vice versa. Okay, the first classification was based on the different devices that we are using, uncontrolled, fully controlled and half controlled. Now the next type of classification is based on what is the direction of power flow, that is unidirectional and bidirectional controllers. Similarly, depending on the power flow, that is what will be the output voltage and output current. Depending on that, we can further classify the rectifiers as one quadrant. If the operation is the voltage is also positive, output current is also positive, in such a case the operation takes place within one quadrant. So, such type of converters are known as single quadrant converters, one quadrant converters. Here converters is nothing but the rectifiers what we are referring to. Next, two quadrant converters. Two quadrant converters, depending on how many devices you are going to use. If you are going to use two devices, okay, two diodes or two thyristors in a circuit, then you will be getting a positive voltage as the output, but the current can be from positive side as well as from negative side. Later when we study the circuits in detail, I will in detail explain how the quadrant lies. Okay. So, for now the rectifiers are also classified as a single quadrant, a two quadrant as well as a four quadrant converters. Okay. So, depending on this, we have the different combination, how this one quadrant, two quadrant and four quadrant, how it is going to look, the power flow, voltage versus the current when we plot the graph, how we are going to get, how it is being spreading out along the graph. Depending on that, we classify as single quadrant, two quadrant and a four quadrant converters. Now, let us see the diagram in detail. So, these are the different circuits for the converters classified based on the quadrant of operation. Now, one quadrant operation means we can either use the thyristor as a device or we can use the diode as a device. Okay. The output that we are going to get, the voltage will be also positive, the current will be also positive. Now, if you are using any one of the device, either you are using one diode or a single thyristor, then we will get the operation where both the IDC is the output current and VDC is the output voltage. Both the VDC as well as the IDC lies in the positive side. When voltage and current both are positive, it is nothing but the first quadrant operation, and here AC to DC is being converted. So, here we can call it as the rectification action. We are converting the input AC to the output DC. Okay. Similarly, when we come to the two quadrant operation, here we are going to use two thyristors. Okay. Two thyristors in anti-parallel manner we will be using. So, when we are using two thyristors, during the operation, that is during one positive half or negative half, depending on the location of the anode and cathode of the thyristors, one thyristor will be kept in such a way that for the positive half cycle it will convert into DC. Okay. So, what will happen? AC is given, thyristor anode is connected, along with the application of gate pulse, we are going to get a DC. So, we will be converting AC to DC, first quadrant operation. Voltage will also be positive and the current IDC will also be positive. Okay. That is the first part, rectifier of the first quadrant. Okay. Next, what will happen? You have another thyristor and back to back, we will be connecting like this. So, the another thyristor will be connected, that is it is going to work when the AC, the input goes to the negative half cycle. So, in the negative half cycle what happens? The current will start flowing. Okay, the current starts flowing from this DC to the AC. Whenever we say DC to AC, that is a inversion action that is taking place. Inversion is nothing but where a DC, the part of the output is being supplied back to its input. Okay, so we call it as voltage output, the current flowing will be the same from this direction, but what will happen? The output voltage what we will be getting will be a negative value. Okay, so the voltage will be negative, but the current will remain the same positive. So, it comes to the fourth quadrant where I is positive, the x axis is positive, y axis is negative. So, it is an inverter action. Okay, when we are using two thyristors in anti-parallel or back to back manner. That is the operation of a 2-quadrant converter. Now, depending on if you are going to use 4 thyristors, okay, if you are going to use 4 thyristors, converter 1 means, here 1 converter means you should have full conversion means 2 thyristors you should use. If you are using either 4 thyristors or a bridge configuration of thyristors, then what will happen? You will get a 4-quadrant conversion, okay. So, one thyristor, one part of the converter will be responsible for the rectification as well as for the inversion action. Similarly, the other converter will also be responsible for the inversion as well as the rectification action. Since we are having 4 different devices connected along the same supply, depending on the input that is given to the depending on the input that is applied across the position of the thyristors, we will get the form of 4, in all the 4 quadrant we will be having the function. That is, converter 1 will be used for rectification as well as for inversion. Similarly, at the same input, converter 2 will also be used. When it is rectifying, it will be doing the inversion operation. When this is rectifying, converter 2 is rectifier, acting as rectifier, converter 1 will be doing the inverting action. So, this is how later when we study the different control rectifier circuits in detail, we will understand how this quadrant operation lies. This is the general classification based on the rectifier circuits. So, next we will be studying about the different control techniques. Control techniques means we know that we have an AC signal, we want to convert it into DC signal. How we are going to achieve this controlling action? That is depending on the various techniques available within the given converter, okay. So, in that we have 3 different type of techniques. That one is known as, the first one, phase angle or firing angle control. Means we have already come across the word firing angle for a thyristor. That is, whenever we are going to give the gate pulse, at which point, we have seen the different gate characteristics also, which indicates that whenever the gate pulse what we are applying, if it reaches the threshold value, only then the thyristor will go to its on state, okay. So, that application is known as, the application of that pulse is known as the firing angle, okay, or it is also known as the phase angle. Using this firing angle, we are going to achieve the control, means what is the amount of output we require. The other type of control strategy or control technique is using extinction angle control, and the third type is PWM control. PWM means we know that it is a pulse width modulation. The width of the pulse is varied. Depending on the width variation, we are going to achieve the controlling action. Okay, so now one by one we will see the different controlling techniques that are being followed for achieving the controlling part in a phase control converter system, or simple we can say that it is a rectifier system. Now, let us assume that we are going to use a single thyristor to an input AC signal, okay, and the control voltage. In the control voltage, you are having initially I said that you can either use a thyristor or a transistor. We prefer the thyristors because of many advantages, okay. One of the advantages, you can just provide the pulse that is required at some instant of time. If you give the pulse, that is going to be sufficient to turn on the gate of the thyristor, to be applied to the gate of the thyristor, which in turn will turn on the thyristor. You can just produce the pulse. Power is being saved. Whereas, if you don't want to use a thyristor, if you want to use only a member of a transistor family such as an IGBT, MOSFET or a BJT, if you are going to use any of the power transistors here, then you have to provide the entire signal. Means the entire time you want to turn on, give the complete signal, okay. So, this level, that is, this is a pulse and this is a complete signal that you are applying. Here loss of power will be more, so usually we prefer the thyristor, okay. Coming back to the control technique here, for an SCR or a gate turn of thyristor, when we are going to give the pulse, this delta is the width of the pulse as well as alpha is the firing angle, as we already know. When the firing angle is applied to the thyristor, the input AC that is being supplied will be getting at the load, that is, input will flow through the switch, the thyristor that we are using, to the load. So input gets connected to the output, and at the output we are going to, this is the output voltage VDC. So at the output we are going to get a DC component. Okay. So this is how we are going to get at the firing angle alpha when you are applying the input signal or the control signal. Till then you will not be getting output because the switch is not on. Switch is not on means the path for the flow of current is not yet established. So you will not get any output voltage from 0 to alpha. Okay. So the output is 0, but once you give the pulse across the gate, so that will in turn turn on the thyristor, and then you will be getting the signal at the output. Okay. So from alpha to pi, whatever the input is there, see the shape of the waveform, it follows the input shape. Okay. So this is what you will be getting. Okay. Similarly, now let us say we have used only one thyristor for ease of understanding. Next, at the instant of 2 pi plus alpha, you are applying the next gate pulse to the thyristor. So again here, till here from pi to 2 pi plus alpha, the line is a straight line. Means we are not turning on the thyristor. Okay. So the straight line indicates that the output is not available, means the switch is in the off condition. Switch is in the off condition means it blocks the flow of current in the circuit. Okay. So next, at 2 pi plus alpha, again when you are applying the pulse across the SCR, or if you are applying the signal across the power transistor family member, so you will be getting the output voltage from 2 pi plus alpha to 3 pi. Okay. So this is how you will be getting how you are going to achieve control. Now controlling means, if you want alpha is equal, let us say this alpha is around 15 degree. Okay. So 15 degree if you are applying, see the output voltage, you are getting a high level of output voltage. Now let us say alpha you are going to apply somewhere around 70 degree. After 70 degree you are going to apply the signal, means you can find the shift in the signal. So here you will be applying the pulses, and the output voltage what you are getting is very small voltage. If you are increasing the firing angle, the output voltage will be a smaller one. So when you are observing or when you do any experiment regarding this SCR and the input voltage, you can clearly observe that whenever the value of the firing angle is more, the value of the output voltage is less. So firing angle and the output voltage are inversely proportional to each other. Now if alpha is small, then what will happen? The output voltage is a bigger one. Now if your alpha is around 75 degree or 80 degree here, then what will happen? This output will be only so much available, little bit output, but the value of alpha is more. So it is vice versa. That is how we are going to achieve control using the concept of firing angle, or it is also known as phase angle control. So this is one of the control technique which we use extensively. Okay. The next type of control technique is extinction angle control. This extinction angle control, extinction angle is used when we are going to use the energy storing devices. Let us say for example we have an inductor. This is an LR load. RL load is connected at the output. Okay. When we say an inductor, we are giving an AC input signal. So we know that whenever an inductor is connected, energy starts storing in the inductor. Okay. So during, let us say, positive half cycle, energy starts storing here, positive negative flows into this. Now when we are switching over from negative cycle to positive cycle, then what will happen? From negative to positive means the inductor, whatever the energy has been stored in the inductor should be released outside. So this releasing of energy will take place, changing the sign, reversal of polarity takes place, and the stored energy in the inductor will be given out. Okay. So this is the general process of the energy storing device. So in the similar case, when we are going to use the energy storing device, when inside a rectifier circuit, then we are going to come across something known as this extinction angle. Later when we study the different circuits of phase control converters with RL load, we will come to know what is this extinction angle. So, this releasing of energy by the inductor which is in the opposite direction, okay, and this energy, the energy stored in the inductor will completely die out. Okay, so that is known as, that part of the waveform is known as the extinction angle. Okay, usually represented as beta. Okay. Now what we are going to do in the extinction angle, now we are going to give the pulse here, okay, when it is a pulse triggered or a level triggered waveform. That is depending on the type of switch, if you are using a pulse triggered or a level triggered, here the rising of the pulse from 0 to 1. Okay, let us say you are going to use a pulse triggered switch and this is the 0 level and this is the 1 level. So, when you are having the rising edge from 0 to 1, whenever it encounters, the input signal encounters a pulse, what will happen? It will stop conducting. Okay, here in case of this, there will be the output voltage available from 0 to this extinction angle, but once when it comes across this pulse, rising edge of the pulse, automatically you will get a 0 output in case of pulse triggered switch. Now, if you are using a level triggered switch, it is the opposite. Level trigger switch, when it is a falling edge, means from 1, when it is falling to 0, during this falling edge, the output voltage will be made 0. It will go to its off state. When you are using a pulse trigger, from 0 to 1, it goes to the off state. That is the rising edge. Whenever it encounters a rising edge pulse, it will go to its off state. If you are using a level triggered switch, then if you are coming, that is a falling edge from 1 to 0, if you are applying in the level triggered switch, then it will be sensitive to the falling edge and the output voltage VDC means the output voltage will go back to 0. Okay. So, this is nothing but, this part is nothing but the beta extinction angle. Later when we study with the RL load, you will clearly understand this type of control action. Okay. Then the next type is PWM. PWM means pulse width modulation controlling action. Pulse width modulation controlling action means here this pulse depends on the value of alpha, firing angle, as well as the firing angle. It also depends on the width of the pulse, delta. Let us say delta is the pulse width. Depending on the pulse width as well as the firing angle, using these two factors, we are going to achieve the PWM control. In all the high applications, high level applications, okay, such as the speed control of motors, industrial heating and all, we make use of the PWM technique and we fix the value, that is depending on the length of the width of the pulse delta as well as the firing angle which is fixed, and it is allowed to do the operation. Usually in industrial purpose, we prefer the pulse width modulation technique of controlling. Now, how this is done? If it is a level trigger, see now, if you are going to give the length of or the width of the pulse from this alpha to some angle alpha minus pi by 2 or alpha minus 180 degree, okay. So, this is the maximum value, this is nothing but pi by 2, 90 degree. So, this point will be delta minus pi by 2 and this will be delta minus pi. So, if you are applying the width of the pulse in such a way that for how long the pulse width is there, so long you will be getting the output voltage. Okay. If you are minimizing, reducing the pulse width, the output voltage will be small. If you are increasing the pulse width, the output voltage will also be for a longer duration. So, depending on the width of the pulse, either you can broaden the pulse or you can narrow the pulse. Depending on that action of the pulse width, we are able to control the output DC voltage. Okay. So, this is how you are going to achieve, using pulse width control technique, you are going to achieve the output voltage. Similarly, if we are going to use the pulse triggered switch, here if you are using pulse triggered switch, then you have to use separately turn on pulses and separately turn off pulses. And we know that whenever we are using a pulse trigger, it is sensitive to the rising edge. So whenever it encounters a rising edge, you will get the output voltage. Whenever it encounters another pulse at the rising edge, that is a turn off pulses. So then you will get the output voltage will end. Okay. So when you are using pulse triggered switch for a PWM control, you should use two different signals. One set of signals should be for the turn on purpose, and the other set of the signal should be for the turn off pulse. So the combination of these two, turn on pulse and turn off pulse, is nothing but the pulse triggered signal. So if you are using this value, now depending on this value, when you are giving the turn on, when you are giving the turn off, the width of the pulse will change. The width of the output voltage will vary. Okay. So varying these values, you can control, you can achieve the control over the output voltage. And this is how, by using the PWM technique, you are going to achieve the output controlling. So in the three different cases, we saw that how we are going to control the output voltage depending on either firing angle, extinction angle, or a PWM, pulse width of the pulse. So these are the three main control strategies which we follow for a phase control converters. Thank you.